Our next topic is to look into different machinery faults that are usually associated with non-synchronous vibration energy. When we say non-synchronous vibrations, it is usually referred to the vibration energy that is not an integer multiple of the fundamental frequency or one-time RPM. So it means the vibration energy at a frequency above one-time RPM, and it could happen at any frequency, and this frequency is not originated from the one-time RPM vibration energy source. The most common faults that are associated to non-synchronous vibration are the anti-friction bearing defects, pitting, resonance, cavitations, belt pulley system faults, and electrical motor faults. Anti-friction bearing or AF bearing is widely used in many machinery, and the common cause of this type of bearing defects are due to pitting or indentations at inner race, outer race, bore, and the bearing cage. Lack of excessive lubrications, looseness due to excessive clearance, assembly errors, and contaminations. It happened that vibration analysis or using vibration as a parameter could help to identify the defect in AF bearings, especially for the defect due to pitting and indentations. It can also use to identify at where the defect is actually happening, for example, inner race, outer race, the bore, and the bearing cage by looking into the frequency that associated or generated from this part when there is a defect. They are bore pass inner race frequencies, BPFI, bore pass outer race frequency, BPFO, bore spin frequency, BSF, and the fundamental train frequency, FTF. Bearing life is usually categorized into 4 stages based on the rated life L10 as listed in the bearing manufacturing catalog. Stage 1 is where more than 70% of the bearings are commonly in these conditions. According to the rated life at catalog, it is noted that the bearing at this stage can usually go for 50,000 hours or 5 years. If the bearing is at stage 2, usually more than 20% fall under this stage could only last less than 1 year or 10,000 hours. If a bearing is in stage 3, it is predicted that the rated life is significantly reduced and it is expected to fail within 3 months. Whereas in the final stage or stage 4, where more than 1% of the bearing are in this stage, is expected to last for only 2 weeks. However, research has found that the actual condition of most the in-service bearings fail at a faster rate than as predicted by the catalog. At stage 4, for example, the bearing can only last less than 4 days. This has made the condition monitoring using vibration become so important to detect the bearing faults before it is actually failed. In vibration analysis, it could identify the defects in AF bearings happen in inner race, outer race, bore, or cage by looking into their respective frequency that is generated from this part when there is a defect. Here, they are referred to as bore pass inner race frequencies, BPFI, to indicate defects at the inner race, bore pass outer race frequencies, BPFO, to detect outer race defect. Bore spin frequency, BSF, is associated to defect at the bore or rolling element, and fundamental train frequencies, FTF, is referred to the defect happen at the bearing cage. In vibration spectrums, whenever there is a AF bearing defects, it will show some indicative fault characteristics in the vibration data. Repetitive impulsive signals are sometimes visible in the vibration time waveform in accelerations. When this signal is transformed to the frequency domain, the vibration spectrum will show broadband rise at high frequency regions. If the bearing is severe enough, usually stage 3 onwards, the bearing frequency or the bearing defect frequencies associated to the respective part as well as their harmonics are usually visible in the spectrums. Side bands around the bearing frequency or bearing natural frequency are sometimes visible so as an indications of the bearing faults. So in determining the bearing defect frequency, usually it requires the physical dimension of the bearings. For example, the pitch and bore diameters, number of bores, and contact angle, as well as the shaft speed. Inserting this information into the formula shown will give you the respective bearing frequencies. Sometimes, the bearing manufacturers also provide the bearing frequencies informations and can be found in their catalog database. In the case of the physical dimensions or manufacturing database is missing, one can approximate the bearing frequency based on the number of balls or rollers. The bearing frequency formulas are suitable for any rolling elements bearings such as ball, rollers, or taper roller. By inserting the running speed in RPM, ball and pitch diameter is in mm, number of rolling elements, and respective contact angle, one can calculate the bearing defect frequencies associated with the inner race, outer race, the ball, and cage defects. In the manufacturer database, one can first find the respective bearing based on the bearing numbers from the manufacturing database. Under each bearing's number, the bearing frequencies are stated in terms of its non-integer multiples. Multiply this bearing frequency of non-integer multiple with the shaft speed, give you the bearing frequency in Hertz or CPM. In analyzing the anti-friction bearing faults in vibration spectrum, usually it can be categorized into 4 stages and 4 zones across the frequency range up to more than 120 kHz. In stage 1, usually the fault can only be detected using HFD or high frequency detection technique because the frequency are usually the ultrasonic frequency which are usually above 120 kHz. In stage 2, the bearing natural frequencies components with side bands are usually visible and can be used to indicate the severity of the bearing defect. If the bearings defect is in stage 3, the appearance of the bearing defect frequencies with the side bands will be observed. On top of this, the amplitude of the natural frequency component with sideband will grow higher. Finally, if the bearing is in stage 4, random broadband high frequency noise floor is usually visible. In this highly severe case, the amplitude at 1 time RPM also increased significantly. It is also observed that in the high frequency component in zone D, the amplitude of the frequency component will grow excessively over the 4 severity stages. This has made the HFD or high frequency detection technique become very popular in detecting bearing faults. Over the years, some technique or diagnostic tools have been developed for bearing faults detection. Most of these tools are utilizing the high frequency detection techniques and with some digital signal processing technique to extract the repetitive impulsive response hidden in high frequency region when there are faults in bearing. Acoustic emissions look into the appearance of high frequency component up to 1000 kHz in the event of faulty bearing. Whereas technique like envelope analysis and other specific technique like spike energies, shock pulse, peak view, and crest factor are utilizing the repetitive impacts created by the faulty bearing in every rotation. For examples, crest factor is utilizing the ratio of peak to RMS values in the repetitive impact response to evaluate the severity of the bearing defects. High crest factor indicate higher peak value or impact created by the faulty bearing, showing high severity. We have also discussed envelope analysis in the digital signal processing technique topics, and it is noted that this technique is very effective in determining faults in the anti-friction bearing gears, journal bearing rubs, and any faults that creating repetitive knocking or impulsive force. Most of the specific bearing faults diagnostic tools developed by different manufacturers in the current markets like Spike Energies, Shocks, Pulse, Peak View are utilizing very similar working principle as in envelope analysis. In one of the bearing defect case studies involving the vibrating screen in the mineral processing industry, the trending of the envelope spectra show an outer race bearing faults as the BPFO frequency components of the bearing is visible at the vibrating screen driven end bearing. In the fifth survey, the increase of level of 1 time RPM also indicated that the bearing defects was probably in stage 4 and in highly severe conditions. It also indicated that the increasing bearing wear over the 5 vibration trending plot. No corrective actions were taken and the bearing seized and burned at the end. In another case study involving the rolling mill machines, abnormal high-pitched noise was first observed. Performing envelope analysis, and it was found that the envelope spectrum show the BPFO and the BSF frequency component. These indicate the defect is at the outer race and rolling elements. The bearing was immediately replaced then.